Welcome to this video on using Hess's law with enthalpies of combustion to find enthalpy changes indirectly. So, considering first this particular reaction taking place here. Now we'd love to be able to calculate the enthalpy change for that reaction. We can't do it directly because the reaction rate's too slow, nor can we use standard enthalpies of formation. And I wonder if you could look at the equation and tell me why. Well, what you should have realized is that this is actually an enthalpy of formation. This is the enthalpy of formation of this compound, propane 1,2-diol. It's forming 1 mole of the substance from its elements and everything in its standard states. So we can't use enthalpies of formation to calculate this indirectly, but for many compounds we can burn them in excess oxygen and calculate or measure the enthalpy of combustion, and these are another really useful means to work out enthalpy changes indirectly. So, brief reminder on standard enthalpies of combustion, using carbon as our example. So this is the heat energy change when 1 mole of a substance, so 1 mole of carbon, is burned completely in oxygen, O2, under standard conditions, with all reactants and products in their standard states. So this should be solid carbon, gaseous oxygen, and gaseous carbon dioxide. Well, propane 1,3-diol is a liquid. That's all I should need to tell you to be able for you to write an equation which corresponds to the standard enthalpy of combustion of it. Pause the video and have a go. Well, here's what you should have got. Propane 1,3-diol is a liquid at room temperature. It's reacting with O2, which is gaseous, to make 3 moles of carbon dioxide and 4 moles of water, and then we've got 6 oxygens there and 4 there, that's 10. 2 over here already, so we need another 8, so we need 4 O2 in order for this to work, and that would correspond to the enthalpy of combustion of this compound. Well, here's the equation here, and we're going to attempt to use Hess's law to work out what that unknown enthalpy change is. So this time using these enthalpy of combustion values. So if we take carbon and we combust it, we're going to make carbon dioxide, as we saw earlier. So that's going to be CO2. And we've taken 3 moles of carbon, so we're going to make 3 moles of carbon dioxide. And that enthalpy change then, the enthalpy of combustion is minus 394. That's for 1 mole, so we need 3 lots of that value if we're going to combust 3 moles. Now hydrogen also will combust, and that's going to make water, and this time we're going to use 4 moles of hydrogen. We're going to make 4 moles of H2O, and so we need to quadruple our enthalpy of combustion, which is shown below. Now when it comes to oxygen, the enthalpy of combustion of oxygen is going to be 0. So this one here is going to have a value of 0. So the enthalpy of combustion of oxygen is 0. But we're still going to have this same oxygen coming down here. And so we've got these products of combustion products this time. And it turns out that if we combust propane 1,3-diol, we're going to get exactly the same products of combustion. Carbon dioxide and water, just as we saw in the equation on this slide. So carbon dioxide and water are our combustion products, and this time we are combusting 1 mole of it, and so 1822.9 is the enthalpy change that we need. So now we've constructed the cycle, we've added on the enthalpy changes. The next step is to find our roots. So this time we look at where the arrows begin, and now all the arrows begin here, and so we've got, and all the arrows end at the combustion products. So we can say that the blue arrows here correspond to one route, and the red arrows correspond to the other route. And if we look, we can see the red arrows are going in a clockwise sense, the blue arrows are all going in an anti-clockwise sense. So we can have our expression of Hess's law, which is that delta H, in this case plus minus 1822.9 must be the same amount of energy change as the blue route, which is 3 times minus 394 plus 4 times minus 286. Because we've got the same starting and finishing points, and therefore the total energy change should be the same. So if we, again, now our final step is to solve. So we've got minus 2326 on this side. We need to subtract from that what was on the right hand side, minus 1822.9, and therefore we find that delta H is equal to minus 503.1. Now, what degree of precision should we give our answer to? Well, this is one of those rare cases where we're adding and subtracting quantities, and so we need to conserve decimal places rather than significant figures. And in this case, we want to try and give our answer to the lowest number of decimal places from the data given. And in this case, we've got some to 0 decimal places and some one value to 1 decimal place. So we want to give our value to the nearest whole number, or 0 decimal places. So minus 503 kilojoules per mole to the nearest whole number. Here's another example for you to practice. This is the enthalpy of formation of benzene here, C6H6. Pause the video and see if you can use the data down here to work out the value of this unknown enthalpy change. Well, let's see how you got on. So we're going to put the combustion products down here. Because we've got enthalpy of combustion given to us. And these are 6 moles of carbon is going to make 6 moles of CO2. 3 moles of hydrogen is going to make 3 H2O. And if we look here, 6 carbons, 6 CO2, 6 hydrogens, 3 H2O. These are the combustion products. So we can then connect up our arrows. 6 times the enthalpy of combustion of carbon, 6 times minus 394, 3 times the enthalpy of combustion of hydrogen, 3 times minus 286, and then 1 times the enthalpy of combustion of benzene. Again, let's look for our routes, or we can think about our clockwise and anti-clockwise arrows. These arrows here are all going one way. They're all going anti-clockwise, or you can think about if this is our starting point and this is our ending point, they're going directly. Or there's the blue route here, which goes from our starting point in a clockwise sense down towards our finishing point. So we've got delta H and minus 3267 along the blue route, or the clockwise route, or the indirect route, and then the direct route, or the anti-clockwise sense of arrows. We've got 6 times minus 394 plus 3 times minus 6. So now we solve for delta H, and we find that all the red enthalpy changes came out at minus 3222. We subtract from that minus 3267, and we find that the value of delta H is plus 45 kilojoules per mole. and that was using enthalpies of combustion to calculate enthalpy changes indirectly.